This is a manufacturer's instructional manual for a centrifugal pump. If you spend just a couple of minutes going through it, or a manual for almost any type of industrial machinery, you'll soon understand how important it is to measure things accurately. Now, to operate correctly, clearances in the pump are to be within thousands, and certain tolerances are specified within tens or hundreds of thousands. Of course, coarse measurement tools like rules and simple calipers can't measure that accurately. For such precision measurements, we need precision tools. Now, as a general rule, the more precise a measurement tool is, the more delicate and expensive it is. So, as we talk about precision measurement tools, we'll be seeing certain precautions to be taken when using and storing them. Precautions like storing them in wooden boxes to protect them from being damaged. The first precision measurement tool we'll be talking about is this one, the Vernier Caliper. The Vernier Caliper gets its name from the 16th century French mathematician Pierre Vernier, who invented the principle this tool is based on. Now, the first thing you might notice is that the Vernier Caliper is very similar to the slide caliper. Like the slide caliper, the Vernier Caliper has a fixed jaw and a sliding jaw that moves along the shank of the frame. The main scale is stamped along the length of the shank. Like the slide caliper, the Vernier Caliper can take inside and outside measurements, but the measurements must be taken using different parts of the scale. On this Vernier Caliper, the upper scale is used for inside measurements, and the lower scale is used for outside measurements. But this arrangement will vary with different Vernier calipers, so when taking measurements, be certain to use the correct scale. The major difference between sliding calipers and Vernier calipers is this second, smaller scale on the sliding jaw. This is the Vernier Scale, and it's what makes this tool a Vernier Caliper. Notice also that there's a special adjustment device attached to the sliding jaw. The adjusting nut at the bottom of this device is a kind of fine-tuning adjustment. Turning the nut one way or the other moves the sliding jaws back and forth very gradually. Using this Vernier Caliper, we can get measurements accurate to 1,000th. And once you learn how to read the small Vernier scale accurately, you can get fairly precise readings for 10,000ths also. So, before we attempt to measure anything, we'd better look at how to read a Vernier scale. Since a real Vernier caliper is too small to see clearly during this demonstration, we've constructed a model. Not all Vernier calipers are identical to this one, but Vernier calipers are similar enough that what we'll learn on this model can be applied to most Vernier calipers you'll work with. Here we have the fixed jaw, the sliding jaw, the main scale, the Vernier scale, and the adjusting device. Let's begin with the main scale. Like other rules we've seen, the main scale is divided into specific units of measurement. This is an English measure Vernier caliper, so the basic unit here is the inch. The large numbers and longest lines represent full inches. You can see that on this particular caliper, there are 10 numbered lines between each set of inch marks. Each of these smaller numbers represents 1/10 of an inch. So, for example, here we have the 1 inch mark, the 1 1/10 inch mark, 1 2/10, 1 3/10, and so on. In turn, each of the tenths is divided in half. Each of these small lines then represents 1/2 tenth or 1/20th of an inch. On the main scale of this caliper then, there are 3 sets of marks. full inches, tenths of inches, and 20ths of inches. This means that the smallest measurement we can make using the main scale is a 20th of an inch. But remember, we said that we want to measure accurately down to thousandths of an inch. To mark off single thousandths on the main scale, we'd have to draw 50 lines within each of these small gradations. The lines would be so close together, it would be almost impossible to read the measurement accurately. When Pierre Vernier tackled this problem almost 400 years ago, the solution he came up with was the Vernier Scale. The Vernier Scale on this model consists of 50 gradations, with every fifth one numbered. Your text explains the scale in detail, but for now we need to know only how it's used to take measurements. Okay, let's say we're measuring the outside diameter on an object, and the jaws of the caliper are now locked in their proper position. Let's take a look at the lower scales, the ones marked outside. We're going to take the reading in 4 parts. The 0 mark on the Vernier scale marks the point where we take our first 3 readings. In this case, the 0 falls between the 2-inch and 3-inch mark on the main scale. So we know that the object measures at least 2 full inches. Next, we count the number of full tenths on the main scale up to the 0 on the Vernier scale. That's 2 tenths. And we can write that down right here. Then we count the number of 20ths between the 2 tenths mark and the 0 mark on the Vernier scale. Here the reading is 1/20th, which equals 5/100ths. That completes the first 3 parts of our measurement. Now we're getting down to the real precision. We're looking to find out how many thousandths there are between this 20th mark and the 0 on the Vernier scale. The way we do this is to search along the Vernier scale until we find the mark that lines up perfectly with any mark on the main scale. So we add, it looks like 11 there to me, we add 11 thousandths to our column of numbers. And we add the numbers up. The complete reading is 2.261 inches. In review, what we've done to get this measurement is to add the number of full inches, tenths of inches, 20ths, and thousandths. Your text explains the procedure in more detail, but before you turn to your text, let's see how a Vernier caliper is used to take a measurement. Since Vernier calipers should always be stored with both the sliding scale and adjusting device locked in place, the first step is to loosen both locking screw nuts so that the sliding jaw can move freely. The jaws are then set at the approximate diameter to be measured, and the caliper is set on the work. By locking the adjusting device in place, the mechanic can make final adjustments to the sliding jaw by turning the horizontal adjusting screw nut at the bottom of the adjusting device. He adjusts the jaws until he feels the right amount of drag between the caliper and the work. His sense of touch tells him when his measurement is correct. He then removes the caliper from the work and locks the sliding jaw in place before taking his reading. So that you can look at the reading on the caliper we just saw, I'll set up an identical reading on the model here. Okay, let's see what we have. Well, we don't have any full inches, but we do have 4/10. In addition, we have 1/20, which equals 5/100. And as we look along the Vernier scale, we see that the looks like 25 line coincides with the line on the main scale. So we know we have 25 thousandths. Adding them together, we get a measurement of 475 thousandths of an inch. That completes our discussion of Vernier calipers, but as we'll see, other precision measurement tools also use the Vernier scale. So take this opportunity to read through section 1 of your text and work out the problems you'll find there. When you feel confident taking accurate readings on the Vernier scale, we'll look at another precision measurement tool that's even more common than the Vernier caliper. These are outside micrometers. You may have seen them used before, and you may have seen them abused before too. Like Vernier calipers, these micrometers, mics as they're commonly called, are delicate and expensive instruments, and they require special care. Keep in mind that mics remain accurate and in good condition only if treated properly. Before we see how an outside micrometer is used, let's talk about its purpose and its parts. Like the Vernier caliper we saw in the last segment, the micrometer is used to measure to the nearest thousandth. The measurement is made between these two parts, the anvil and the spindle. The spindle can be locked into place with this lock nut. The section here is called the sleeve. Stamped or engraved in the sleeve is the main scale. And the part that rotates on the sleeve is the thimble. Rotating the thimble in one direction moves the spindle toward the anvil. Rotating it in the other direction moves it away from the anvil. As you can see, the thimble has a scale along its beveled edge. This flat curved part that connects the anvil to the rest of the mic is the frame. The frame provides a handle to hold while taking measurements. Typically, outside micrometers are referred to by size. Here we have 3 different size mics. Now this is a 1-inch outside mic. It can measure only dimensions from 0 to 1 inch. Over here we have a 2-inch mic, on the other hand, which measures only dimensions between 1 and 2 inches. And this 3-inch mic measures only from 2 to 3 inches. Outside micrometers are made as large as 24 inches, but most of them have a range of only 1 inch. So, for example, an 18-inch micrometer can measure only dimensions between 17 and 18 inches. This means that the first thing you have to do to take a measurement is to guesstimate to the nearest inch the size of the work you're measuring. Then you can select the correct micrometer to do the job. When taking measurements with an outside mic, it's important that you hold the tool in a comfortable position. a position that allows you to turn the thimble as well as the work you're measuring. Depending on the size of your hand, mics up to about 5 inches are most easily held like this. My last 2 fingers are hooked through the frame, freeing my thumb and forefinger to turn the knurled nut or the thimble. Also, the other hand is free to hold the object I'm measuring and to work the lock nut. Okay, now let's watch the correct procedure for measuring round stock with an outside mic. Since the stock we'll be measuring is less than 1 inch in diameter, the mechanic selects the 1-inch mic for the job. To prevent their being damaged, the moving parts of micrometers should always be locked in storage, so the first step is to unlock the thimble and spindle. Then he opens the tool to approximately the diameter he's measuring. Holding the mic properly, he sets the work between the anvil and the spindle. Then he turns the knurled nut until a slight pressure indicates that spindle and anvil are in contact with the widest part of the work. He then locks the spindle in position and removes the mic to take a reading. Once the reading is made, he unlocks the spindle and returns it to its storage position. Notice that he doesn't tighten the spindle against the anvil. He leaves a slight gap in case the metal expands in storage. Then he locks the moving parts and sets the tool back in its wooden box. To prevent over-tightening the spindle against the work, you can use a mic that has a ratchet stop at the end of the thimble. The ratchet stop is designed to slip with a loud click when the pressure of the spindle against the surface is just right. When you hear that click, you know that the spindle is in proper position. The ratchet stop can, of course, be used when measuring flat surfaces as well, but there's not as much danger of accidentally over-tightening the spindle against a flat surface. This is because on flat surfaces, the entire face of both the anvil and the spindle are in contact with the surface and the pressure is distributed evenly. Well, now that we've seen how to use an outside mic correctly, how do we read a micrometer? Again, to make the procedure easier to see, we'll use a working model. Before we take a reading, let's spend a few minutes studying the 2 scales on this micrometer. First, there's the main scale on the sleeve. The main scale runs from 0 up to 10 along this line, called the reading line. Of course, with the micrometer set like this, we can only see the first 2 numbered lines. Each numbered line represents 1/10 of an inch. So, for example, here we have 0, 1/10, 2/10, and so on. In turn, each tenth is divided into 4 equal parts, each 25 thousandths of an inch. Now, what about the thimble scale? The thimble scale starts at 0, and each gradation is exactly 1/1000th. Right now, the 0 line on the scale is even with the reading line, so the reading is 0 thousandths. Now it reads 1/1000th, 2/1000ths, 3/1000ths, and so on. The scale goes up to 25 thousandths, which brings the reading back to 0. Now, all this might seem complicated and confusing, but let's set the micrometer at 0 and start at the beginning. Just take a moment to wind it down. All right, we're almost there. Okay, 0. Okay, when the 0 on the thimble scale is even with the reading line at 0 on the main scale. The distance between the spindle and the anvil is 0. When I turn the thimble so that the first mark lines up with the reading line, the distance between the spindle and anvil is 1/1000th. Now it's 2/1000ths, 3/1000ths, 4/1000ths, 5/1000ths, 10/1000ths, 15/1000ths, 20/1000ths, and 25/1000ths, which brings the thimble scale back to 0. Remember, we said that the marks on the main scale are 25/1000ths apart. So it shouldn't surprise us to find that when the thimble reads 25/1000ths, the thimble scale lines up exactly with the first mark on the main scale. And going on from this point, we have 26/1000ths, 27/1000ths, 30/1000ths, and when we reach 50/1000ths, the 0 on the thimble lines up with the second line on the main scale. So far, so good. We know that each complete turn of the thimble moves the thimble exactly 25/1000ths along the main scale. So our next complete turn takes us up to 75/1000ths, the third mark on the main scale. And our fourth turn then takes us up to 100/1000ths, the first 1/10th mark on the main scale. One experienced mechanic told me that the way he learned how to read a micrometer was by the spare change method. He told me to think of each thousandth as a penny. Just as every dollar is 100 pennies, every numbered gradation on the main scale is 100/1000ths. And just as every quarter equals 25 pennies, each of the 4 smaller gradations is 25/1000ths. In effect, then, the thimble counts individual pennies. So here we have $1, 1 quarter, and 10 pennies. That's $1.35, or 135/1000ths of an inch. Your text has exercises to help you learn to read a micrometer accurately to the nearest thousandth. It also includes information on Vernier micrometers, which have Vernier scales that give precise readings in 10/1000ths. So, now that we've talked about how to use an outside micrometer, take some time out, look it up in your text, go over it. Any questions you have, take them to your instructor and have him clear them up. Now, all the micrometers we've seen so far can be used to measure only outside dimensions, but you need to be able to measure inside dimensions also, as well as the depth of holes and recesses. For those types of measurements, you need these tools: an inside micrometer and a depth micrometer. As you can see, both types have the same types of scales as the outside mics we've already seen: a main scale and a thimble scale. This means that they're read basically the same way as outside micrometers are. Let's look at the inside micrometer first. The way it is here, with the thimble and main scales aligned at 0, the mic is exactly 2 inches long. This means that 2 inches is the smallest diameter this inside micrometer can measure. If we turn the thimble all the way to the end of the main scale, it'll take us a couple of seconds to get that done. Okay, 3, 5. The spindle scale only goes up to 5/10 or 1/2 inch. So actually, the way it is here, this micrometer can measure only dimensions between 2 and 2.5 inches. That hardly makes it a versatile tool. What, for example, would you use to measure an inside dimension between 2.5 and 3 inches? You'd use one of these extensions. We know that the mic, the way it is, will measure from 2 to 2.5 inches. So to measure something between 2.5 and 3 inches, we need a 1/2 inch extension. We loosen the locking nut here, slide this rod out of the mic, slip on the 1/2 inch collar, and lock that rod back in place. Now we can measure dimensions between 2.5 and 3 inches. How about 3 to 3.5 inches? Well, just select the rod marked 3 inches to 4 inches and insert it in the mic. To measure 4 to 4.5 inches, add that 1/2 inch collar to the rod. So before you can measure anything with an inside micrometer, you have to estimate the diameter you're going to measure and be sure to select the right rod. That tells us the basic procedure for measuring with an inside micrometer. Now, let's watch it done. Here the mechanic is going to measure an inside diameter. First, he takes a coarse measurement with a rule. We can see that it's somewhere between 3 and 3.5 inches. When he selects a rod, then he makes sure it's the right length for measuring dimensions between 3 and 3.5 inches. Each rod in the set he's using is stamped with its specific range. He then inserts the rod and locks it into place to prevent it from slipping during the measurement procedure. He also unlocks the thimble so that it can move freely along the sleeve. When the mic is in place inside the pipe, he begins turning the thimble counterclockwise. Notice that on an inside micrometer, the rod does not move. Only the thimble moves along the sleeve, expanding the total length of the mic. He turns the thimble until the ends of the mic are snugly against directly opposite points. He rocks the mic back and forth from side to side to find the true diameter, turning the thimble as necessary to adjust the length of the mic. When his sense of touch tells him that he has the true measurement, he removes the mic from the work. He then locks the thimble to prevent it from shifting and losing the measurement, and takes a reading on the scale. Measurements are read on an inside mic the same way they are on an outside mic. Just know the length of the extension or extensions you're using, and be sure to add that length to the reading on the scales. The micrometer depth gauge, or depth mic, also uses a system of extension rods. So the procedure for using a depth mic is very similar to the procedure for using an inside mic. First, use a depth rule to get a coarse measurement of the depth of the hole. Then insert the rod you need into the mic. On this particular depth mic, the rod is inserted by removing the ratchet at the top. Put it back in, and we're all set to take our measurement. Before inserting the rod into the hole, adjust the mic so that the length of rod is less than the coarse measurement you took. This ensures that the tip of the rod will not scrape bottom and possibly be damaged. Then insert the rod in the hole and hold the base of the crosspiece firmly and evenly against the lip of the opening. Since the mic he's using has a ratchet stop, he simply turns the ratchet stop until a loud click tells him that the tip of the rod has reached bottom. Then he locks the rod in position and removes the mic to take this reading. Now, reading a depth mic is different from reading an outside or inside mic. This is because the scale is reversed on a depth mic. Instead of reading from 0 to 10, the main scale reads from 10 to 0. This means that the section of the scale you're actually reading is covered by the thimble. So, for example, the reading on this mic is 675 thousandths, one full gradation short of 7/10. Again, your text has exercises you can do to build your skill at reading depth micrometers. In the last two segments, we've seen the outside mic, the depth mic, the inside mic, and we've watched demonstrations of how to use each one properly. But there's still a lot we haven't covered. Notice, for example, that like other precision measurement tools, micrometers are stored in boxes to protect them in storage. And we haven't mentioned anything about checking the accuracy of a micrometer before using it, a very important point. We'll discuss these points in another segment on care and calibration. But right now, turn off the videotape and read through the micrometers section of your text. When you're finished working through the exercises, your instructor will review your answers and discuss any questions you might have. Besides the Vernier caliper and the various micrometers we've looked at so far, there are other types of precision measurement tools that have moving parts. In this segment, we'll talk about two of them: the telescoping gauge and the dial indicator. Each of these tools measures something different. The telescoping gauge, or snap gauge as it's sometimes called, is used to measure inside dimensions. The cross arms at the end of the handle retract and expand, giving the telescoping gauge its name. Now, these cross arms can be locked into position by twisting the base of the handle like you would in an old-fashioned razor. There. Telescoping gauges come in a variety of sizes, each with a specific range. This one has a range of 1 1/4 inches to 2 1/8 inches. And they're available with cross arms that can measure inside diameters from as small as 5/16 of an inch or as large as 6 inches. Another feature that you should be aware of is that the ends of the cross arms here are rounded. This rounding enables them to fit against curved surfaces, such as the inside walls of pipes and machine parts. The rounded ends also help in finding the true diameter of the part you're measuring. To show you what I mean, let's measure the inside diameter of this coupling hub. First, I unlock the cross arms and squeeze it to fit inside the hub. Then I lock the cross arm and insert it in place. Notice that I position the cross arm so that one end is slightly higher than the other. As I unlock the cross arms, it expands until its ends touch opposite points. Because the ends of the cross arms are rounded, as we saw before, the cross arms find the widest dimensions almost automatically. I can pull the lower end of the cross arms upward like this. When the ends of the cross arms are directly opposite one another, the cross arms have retracted to fit the dimensions of the hub. The lock is then tightened just enough to hold the cross arms in that position while I remove the gauge from the work. Now that I've tightened the lock to hold the measurement securely, how can I take a reading with an outside mic? Following the same procedure I normally would when using a mic, I measure the length of the cross arms, inserting it right in there like that. Telescoping gauges are particularly useful in applications where a regular inside micrometer is too large or too awkward to use. Now, the dial indicator is used to take a different type of measurement. It's designed to measure changes in dimension. To see what I mean, let's look at the parts and functions of this dial indicator. Here, of course, is the dial. This one is graduated in thousandths, which is the most commonly used graduation. Although you probably won't be using one, some dial indicators can accurately measure in 50 millionths. Using the outside ring here, you can rotate the face of the dial to adjust to reading anything you want. We'll see why that's useful in just a minute. Now, the stem extending from the dial is the part that actually takes the measurement. You can see that as I depress the stem, the distance the stem moves registers in thousandths on the dial. By mounting the dial indicator in a stand like this one with a magnetic base, the dial is held steady during measurement. Magnetic base stands are not the only types you can use. In many cases, you can use a stand that clamps to the work or a work table. What kind of things do you measure with a dial indicator? One of the most common uses for a dial indicator is taking run-out readings on shafts and other rotating parts. A run-out reading is a measurement that checks the straightness or roundness of a rotating part. Here, for example, the mechanic is taking a run-out reading on a rotor from a screw-type pump. He first mounts the rotor on a pair of V-blocks. Then he sets the dial indicator and stand near one end of the rotor, pressing the stem of the indicator against the rotor until he gets a reading of at least 5 thousandths. He then sets the dial indicator to 0, or zeros it, as the procedure is called. With the rotor in place and the dial zeroed, all he does is slowly rotate the rotor, keeping an eye on the dial. Any change in the reading indicates some irregularity in the rotor. A slow movement of the needle usually indicates that the part is bent or out of round. After taking a reading at one end, he repeats the procedure at the other, again being sure to press the stem of the indicator against the rotor and then zero the dial before starting. This rotor seems to be in pretty good shape. Of course, the part you're taking a run-out reading on doesn't have to be mounted on V-blocks. Here, the run-out of a coupling hub is being checked with the hub in place on the motor shaft. The part you're measuring can also be mounted in a lathe, but remember to rotate the part by hand. Never try taking a run-out reading on an operating piece of equipment. You'll end up damaging the dial indicator and possibly yourself. Always shut the equipment down, and if necessary, tag it out to prevent it from being started up accidentally. Now, as with other precision measurement tools, the metal parts of a dial indicator should be cleaned with a lightly oiled rag after use. The film of oil helps to protect the metal from corrosion. A dial indicator should also be stored in its special case to prevent it from banging around. Aside from additional material you'll find in your text, that pretty well covers telescoping gauges and dial indicators. It also brings us to the end of our discussion of precision measurement tools that have moving parts. The tools we'll see in the next segment have no moving parts, but as we'll see, that doesn't prevent them from giving accurate measurements. All of the precision measuring tools that we've discussed so far have moving parts. Micrometers have spindles and thimbles. Vernier calipers have sliding scales. Telescoping gauges have retractable cross arms, and so on. But several types of precision measurement tools have no moving parts. Because of this, they're called fixed measurement gauges. These are the fixed gauges we'll talk about in this segment. The thickness or feeler gauge, the taper or wedge gauge, the thread gauge or screw pitch gauge, the wire and sheet metal gauge, and the go, no-go gauge. Each has a different use, as we'll see. Let's begin with the thickness or feeler gauge. The thickness gauge is really a set of thin metal blades. Each blade is precisely machined to an exact thickness, and the thickness of each blade is stamped right on it. To measure the clearance between these coupling hubs, for example, the mechanic first selects a combination of blades that approximates the dimensions of the gap. His first combination is too thick to fit between the hubs, and he doesn't force the blades into the gap. Forcing them could damage the blades, ruining them permanently. On his second try, the combination is not thick enough to fill the space. For an accurate reading, the blade should fit snugly in the space being measured. By trial and error, he's found the right combination of blades. The gauge doesn't have to be forced into the gap, and at the same time, the blades fill the gap snugly. Now, there are two ways to take a reading from a feeler gauge: by adding up the values stamped on each blade, or by measuring the blade combination with an outside mic. Using an outside mic is usually quicker, easier, and more accurate than the arithmetic method. There's one important thing to remember about feeler gauges. They're pretty fragile. Some of the blades are as thin as a single thousandth of an inch, so you have to be careful to protect them against damage like scratches, nicks, or dents that can affect their accuracy. When measuring with a feeler gauge, never force blades into a gap, and don't bend or twist the blades out of shape. When you're finished with the gauge, fold the blades back into the handle to protect them. And don't forget to give the blades a light coat of oil once in a while. Another way to measure clearances is to use a taper gauge or wedge gauge. As its name tells us, the taper gauge is a carefully tapered piece of metal with a scale stamped on each side. The taper gauge is used in much the same way as a feeler gauge, by inserting it between two surfaces to measure the space between them. In measuring the distance between two coupling hubs, for example, the gauge is inserted thin end first between the hub faces, with the gauge in position as far as it will go into the gap. The reading can be taken at the point where the outer edge of the hub touches the gauge. Like the other measurement tools we've seen, taper gauges come in a variety of sizes and are available for measuring in both English and metric units. The screw pitch gauge is similar to the feeler gauge in that it also has a number of blades, but as you can see, these blades are lined on one edge with small teeth. The teeth are used to determine the number of threads to the inch on screws and other threaded fasteners. If I want to know how many threads per inch this screw has, for instance, all I do is to find the blade that fits the threads perfectly. And let me see, I'll guess 11 here. Okay. The best way to be sure you have a perfect match is to hold the screw and gauge up to the light. You know you have the right blade when no light shows between the gauge and the threads. Once the right blade is located, just read the number stamped on the side of the blade. This number, 11 in this case, tells you the number of threads per inch, so I know that this screw has 11 threads per inch. Like the feeler gauge, the screw pitch gauge should be used properly and protected from damage. Avoid using the blades as screwdrivers or small pry bars, and after using them, fold them up and store them properly. The next measurement tool on our list is this one, the wire and sheet metal gauge. A wire and sheet metal gauge is either a disc or a thick blade, like this one, with carefully machined slots along its edge. On one side, the slots are labeled with their width in decimal parts of an inch. On the other side, the slots are labeled with gauge equivalents. Now, there are different gauging system gauges for different types of metals. This one is a Birmingham standard gauge, used only on iron wire and rolled sheet steel. So the gauge equivalents stamped on it are Birmingham equivalents. Your text has more information concerning systems for gauging wire and sheet metal. But for now, let's just concentrate on learning how to use this gauge. To measure the thickness of this piece of sheet metal, for instance, I first check the metal to be sure it has no burrs or other surface irregularities. Burrs, nicks, and corrosion all affect the accuracy of the measurement, so it's important that your first step always be to check the metal you're measuring. Then I locate the slot on the edge of the gauge that the metal fits into properly. That looks like a fit. The metal must fit snugly, but it must never be forced into the gauge. Okay, that looks like the right fit. Now I can find the thickness of the sheet metal in inches by looking at the number stamped next to the slot. 2/100ths of an inch. If I flip the gauge over, I find the equivalent Birmingham gauge value stamped next to the slot on the other side. So I know that this piece of sheet steel is 25 gauge. Now wire is measured in the same way. Just find the slot that the wire fits into snugly. Remember, though, that the wire is supposed to fit in the slot at the edge of the gauge, not in the hole. Only the edge of the slot can give you an accurate measurement. Once I find the right slot, I look on one side of the gauge for the actual thickness of the wire in inches. In this case, 25 thousandths of an inch. And then I flip the gauge over and find out that the gauge equivalent is 23. So, when measuring the thickness of wire or sheet metal, remember two things. First, be sure the metal or wire you're measuring is clean and free of burrs, nicks, and other irregularities. And second, pick the right gauge for the job. Select a gauge designed to measure the type of metal you're working with and one that gives readings in the correct gauging system. That brings us to the go, no-go gauge. Go, no-go gauges are specifically for certain pieces of equipment. This particular gauge is made for one purpose only, to check the inside dimension of boiler tube orifices. The measurement of the orifice is taken with the graduated section at the end. The first step represents the smallest diameter the orifice can be and still be within specifications. The next step represents the largest diameter the orifice can be according to specifications. So when using the gauge, we know that if this part, the go part, fits into the opening is not too small. But if the second step, the no-go part, fits, then the tube orifice is too large. Here, the go part fits the tube properly, but the no-go part does not. So the orifice being checked is within specifications. As I mentioned a moment ago, go, no-go gauges are manufactured for specific pieces of equipment. They're not designed to measure all equipment dimensions, and they aren't all this size or shape. That concludes our list of fixed gauges. We've seen the thickness gauge, the wedge gauge, the screw pitch gauge, the wire and sheet metal gauge, and the go-no-go gauge. As I mentioned before, the thing that makes these tools fixed gauges is the fact that they take readings without moving parts. These aren't the only fixed gauges you'll be using, though. There are dozens of other measurement tools that you'll learn to use as you spend more time on the job. But there is one general rule that applies to all precision measurement tools, whether they're fixed or have moving parts. That rule is, keep them in good shape. In the next segment, we'll see what that means. Throughout this unit, we've looked at several types of precision measurement tools and seen how they're used to take accurate measurements. But one question we haven't answered is, how do you know that the measurement tool you're using is accurate? It could be damaged or could have been banged around so that it's no longer precise. Now, coarse measurement tools like rules and tapes can be checked by simply inspecting the edges and making sure they have no bends or kinks in them. You don't have to worry about the gradations being inaccurate as long as the tool itself is in good condition. But how can you tell whether or not a Vernier caliper is accurate when you go to use it? How can you tell if the scales are properly aligned? The same is true for micrometers. How can you tell whether or not a micrometer is accurate? To answer these questions, for the next few minutes, we're going to talk about calibration. Calibration is the procedure for checking the accuracy of measurement tools and restoring their accuracy if you find them out of whack in some way. Rules concerning calibration vary from plant to plant. In some, mechanics are largely responsible for calibration. In others, only trained specialists are permitted to adjust precision measurement tools. So be sure you know your plant's procedures before attempting the calibration of any tool. The tools we'll use to check the accuracy of our measuring instruments are standards, like this one. It's precisely machined to be exactly 1 inch in length. So, by measuring this standard with some of our tools here, we'll be able to tell whether or not each tool is accurate. This standard is pretty accurate, but for the kind of precision needed in laboratories and similar situations, standards like this one are not accurate enough. For those applications, block gauges are used to calibrate measurement tools. Block gauges are machined under the most exacting conditions, resulting in amazing precision and reliability. For this reason, block gauges like these are found in laboratories and other places where only the most reliable measurements are acceptable. For our purposes, however, any standard, as long as it's in good condition, is all we need. Here, the mechanic is checking the accuracy of an outside micrometer. He places another type of standard between the anvil and spindle and proceeds to measure it just as he would measure any other object. The reading he gets shows that the micrometer is off exactly 2 thousandths. To correct the error, he uses a small spanner wrench supplied by the manufacturer. The wrench fits into a small hole in the sleeve, enabling him to turn the sleeve until the scales are aligned correctly. After correcting the error, he checks his work by measuring the standard again. Right on the nose. Calibration of an inside mic doesn't require a standard or block gauge. First, the inside mic without its extension rod is set at 0 and the thimble is locked into place. The inside mic is then measured with a calibrated outside mic. The reading on the outside mic should match the number stamped on the inside mic. In this case, 1 573 thousandths of an inch. If an error is found, a small wrench, usually supplied by the manufacturer, is used to adjust the nut at the base of the mic and make the correction. Then the inside mic is measured once again and the procedure repeated until its length matches the manufacturer's specification. That shows how to calibrate inside and outside mics, but what about vernier calipers? Well, a vernier caliper can also be checked with a standard, but the accuracy of a caliper can be checked by simply moving the jaws against one another and being sure the scales read exactly 0. If they don't, the caliper is inaccurate and must be calibrated by loosening the screws that hold the vernier scale in place and moving the vernier until the 0 marks match. Other techniques for checking the accuracy of vernier calipers are covered in your text. Dial indicators also must be calibrated regularly, but calibrating them demands skill and equipment found only in your plant's instrument shop. Remember that proper calibration of measurement tools is vital to precision measurement, so follow your plant's calibration procedure. If you're responsible for calibration, then make it a habit to check each tool before using it. If, on the other hand, the tools in your plant are calibrated only by a specialist, be sure the tools you use receive their regular calibration checks. But no matter what the calibration procedure at your plant, the best way to keep your measurement tools calibrated is to take good care of them. This means both handling them properly and storing them properly. Store precision measurement tools in wooden or padded boxes where they can't be accidentally nicked, jarred, or otherwise damaged. Keep all your tools clean by wiping them after use. A little oil on the rag will put a protective film on metal parts, preventing corrosion. Just be sure that the coat of oil isn't so heavy that dirt and grime can get trapped in it. Dirt and grit can easily ruin precision instruments by working their way into moving parts. And here's a tip many mechanics don't think about. When storing micrometers and vernier calipers, don't leave them set at 0. Vernier calipers and micrometers should be stored with their measuring surfaces apart so that the metal has room to expand and contract with changes in temperature. And while we're on the subject of temperature, be certain to keep your precision tools away from extremes of heat or cold that change their size and affect your measurements. And don't forget that, like other instruments, measurement tools with moving parts must be lubricated regularly, but always follow the manufacturer's instructions. Basically, then, there are 3 rules that apply to all measurement tools. First, be sure the tool is accurate and in good shape before every job. Second, use them properly and handle them like the precision instruments they are. And third, always clean your tools after using them and be certain to store them properly. By following these 3 rules and practicing proper measuring methods, your measurements will be reliable. And reliable measurements are the first step toward avoiding costly and time-consuming errors. So learn all you can about these tools and all the measurement tools you'll have the opportunity to use. They can make your job easier and give your work a truly professional quality.